Hello and welcome. In this session, we will talk briefly about the current state of data management solutions. We will go over legacy systems, key technologies that have become quite pervasive in the last 10 years or so, as well as the challenges and limitations that have led to current trends and latest developments. I will briefly discuss IBM's view and overall perspective, and we will see a short demo of one of the leading edge technologies IBM is bringing to market as part of the evolution of data management. So let's start with a most traditional data ecosystem. And this is a chart that I borrowed from Gartner. So traditional, in fact, that some view it as legacy already. On the left, you have transactional systems or operational systems. In the middle, you have your analytic space, your data warehouses, and both feed data consumers on the right for analytics and business intelligence. Tools, for example, like Cognos, Tableau, and even humans, data scientists that are accessing and running analytics on the data. And fundamentally, you have ETL processes that copy, move, and transform data all the way along to the final consumer. The most interesting area, and the one I'm going to focus on in this presentation, is really the analytics space. And what we see here is on the left, we have your traditional data warehouses that implement proprietary binary data formats with storage models that are tightly coupled with your compute in order to give you highest performance and scalability. These solutions implement full asset properties as well as fully support transactional workloads. And then on the right, you have technologies, in particular open source, more specifically Hadoop, that have really come to the rescue of data warehousing and data analytics at scale. I'm talking more specifically about the open source Hadoop technologies that have enabled us to implement data lakes. A data lake is a centralized repository that allows you to store all of your structure and even unstructured data at any scale. They were implemented and they have been implemented primarily on premises using commodity hardware and open source. Their promise was of a cost-effective data management solution for data at really any scale. So what we have today in most common enterprise data ecosystems is both coexisting. The traditional data warehouses on the left with your centralized data lakes on the right. And in fact, one of the primary usage scenarios of data lakes today is for data warehouse offloading. What's important is the ETL process in the middle that again moves data from the more expensive data stores like the data warehouse to the large scale, much more cost effective data lake on the right. Even with this type of ecosystem for data analytics, if we fast forward to the last 2 to 3 years, there are some very important challenges that have emerged. And primarily the trend is for a convergence of data stores. And let's explore why. So Hadoop-based data lakes have been complex and very difficult to maintain. They are vast ecosystems with a multitude of different solutions, and it is difficult, it is complex to support, administer, manage them in a single ecosystem, a single cluster. Ultimately, they have shown to lack the performance needed for reporting, like business intelligence, and they suffer from the data reliability issues, which arise from poor quality and data consistency. At the same time, warehouses have remained very rigid and expensive. They're very expensive to store large data sets. They cannot handle unstructured or semi-structured data and really have a hard time supporting open data formats for the most part. And the ETL jobs to feed data into the warehouse remain costly. In ecosystems where the two have coexisted, um, the two have never really worked well together. They remain expensive as two separate, distinct solutions. Uh, it takes a great deal of effort to get reasonable performance and valuable insights from the data. And it's complex to manage multiple storage systems, different dialects, and the multitude of ETL steps that are necessary to move the data or consolidate the data on a regular basis from the data warehouse to the data lake. You still have the challenge of having hotter, warmer data on the data warehouses that cannot be analyzed, cannot be consumed effectively on the data lake, which is the cold storage, until again that data is ETL over into the data lake. As a result, we view this type of architecture really as legacy today. And a fundamental trend that we're seeing is that we're moving towards a more modern architecture, one where fundamentally the compute is physically, truly and fully separate from the storage. So let's take a closer look at why this modern architecture proposed is advantageous over more monolithic architectures of the past. You still need data ingest, data load that brings the data into your store, hopefully allowing you to catalog that data and classify it in a way that makes it readily consumable by your data consumers. They can go and look for the data, discover it, find it, understand it, contextualize it, and immediately govern it properly and make it available immediately to the data consumers. One of the fundamental changes is the move towards more cost-effective, endlessly or highly scalable storage solutions that support effectively open source data formats uh, and that are available both on premises, private clouds, or public clouds. And then completely separate from that storage is your query engine. And your query engine, essentially what you're doing is you're abstracting the data access layer from your storage, allowing you to virtualize over the data and to offer SQL over the structured data in these data lakes, approximating warehouse grade performance. This is a fundamental requirement for you to offload from traditional warehouses. And last but not least, this query engine abstracted from your storage, separate from your storage, becomes a single entry point for all types of workloads into your data. But fundamentally, even this modern architecture remains a centralized system, a system that entails consolidation of all of your data from multiple data sources into a single data store or data repository. If we look at the market today, data lakes, data lakehouses remain at a crossroads. Why? Because companies are demanding modern alternatives that offer still the promise or the benefits of data lakes, but in containerized environments with cloud native architectures. They want to be able to run the systems on private or public clouds. They want these platforms to be truly multi-tenant, not just for multiple users, but for multiple services. And Hadoop faltering due to open source complexity, too many widgets to grapple with, um, service multi-tenancy entanglement, and the fact that still to be able to gain the most performance and scalability, there's a form of co-location of compute with the data in HDFS to achieve, again, maximum performance and scalability. So it is not true that the compute solutions are truly physically separate. They run most often, whether it's on the data nodes or on an edge node, on the same Hadoop cluster. So companies demand alternatives to these traditional on-premises data lake, lakehouse solutions. And if we look at the industry in particular the enterprises behind Hadoop solutions and Hadoop distributions, we have seen mergers, consolidation of these enterprises over the last few years. So it leaves customers wondering, where do they go next? What is the future of this technology? In order to answer that question, I think we need to take a holistic approach and take stock of the reality in the market today. So let's explore that next. A fundamental fact that I think we're all acknowledging for large enterprises in particular is that the enterprise is fundamentally a hybrid enterprise. What does this mean? It means that customers today have data lakes, data warehouses, on-premises databases and applications, but they also have data stores and are consuming solutions on cloud, not just on one cloud, but on multiple clouds. So attempts to centralize everything fizzle. The move to cloud, the journey to cloud is really a multi-cloud story with all of the complexities that that entails. And on-premise data stores, in particular for companies that have large-scale data into the petabytes, will still be there for years to come. It is very difficult, very expensive, very disruptive to migrate data of that scale into another platform, into another format, into another compute solution. So the fact remains these on-premises systems will remain on-premises for still a while longer. Trying to then implement enterprise use cases in such a complex ecosystem of heterogeneous data stores and data sources, potentially geographically dispersed, it's a real challenge. There's increasingly compliance challenges around governance and security of the data. The governance and security risks in this hybrid, heterogeneous, as I said, potentially geographically dispersed ecosystems, the risks have increased. Trying to integrate data obviously comes at a much higher cost. And unfortunately, these challenges moves us in the opposite direction of business self-service. And it translates into slower time to value for solutions. So what is the answer? The answer, it's a new design, a new architecture, one that fundamentally accepts and embraces the fact that most companies live in a hybrid environment. And what it entails is introduction of an abstraction layer to share and use the data with data and AI governance implemented across the entire hybrid cloud landscape. This doesn't mean that the pendulum now swings from everything centralized to everything decentralized. Like everything in life, it's a compromise. There are cases and usage scenarios and requirements for centralized solutions, as well as other solutions that lend themselves well or optimally when decentralized. And a good example is you can think of all of these different solutions, in particular compute and solutions and data stores. They have a need to have their own meta stores. They have to keep their own metadata, and they do this using their own embedded organic data catalogs. But at the data fabric level, across the landscape, there is a fundamental need for a single global catalog that becomes your single source of truth. It doesn't mean this catalog is a central, singular, unique solution. It can be implemented as a federation of catalogs, but the need is still there for a single global catalog that can act across the hybrid landscape as a single source of truth. And you may be wondering, in that case, what does that mean for data access? Do I still have to go to each of these data sources to access the data separately? Do I have to ETL it into some new central repository where I can then point my data consumers to? What is the solution? This brings us into what we call our data fabric query engine. And this picture is somewhat of an oversimplification, but hopefully it does illustrate the main concepts. And this begins with users that connect to what we call a data virtualization layer. Data virtualization becomes a single pane of glass over your entire ecosystem of data. It enables you to implement governance and security in your SQL engines in one place, in a central place. And what the data virtualization layer really abstracts is your multitude of different data stores and data solutions. You still have your traditional data lakes on the left, you have your operational systems in the middle, you have your object stores, local private cloud, public cloud across multiple public clouds on the right. And how you complete the puzzle, you have four fundamental components. You have, in order to implement a data virtualization layer, your Fabric query engine, you need first and foremost the ability to access data across all of these heterogeneous data sources. That traditionally has been referred to as smart federation, where you can maximize push down of queries to the remote data sources as to do most of the compute and the I/O on the systems themselves, so as to minimize the data that flows back over the network, which happens to be more often than not the most expensive part of the equation. With built-in drivers that know how to connect to those data sources, with caching technologies that allow you to, where necessary and require, cache the most frequently accessed data to speed up execution of your queries. You couple this with a SQL engine that allows you to achieve ever so more stringent SLA requirements, that allows you to achieve the necessary performance, that properly manages the resources that have been assigned to the engine, that enables you to implement an abstraction, views over your data. Governance becomes critical. Having access to the data is only half of the story. How do you know you can trust the data? This is where governance comes into play. A proper data catalog, the ability to create abstractions over your physical data using your own business terminology, understanding and properly producing data lineage, and then applying the processes that are key to governance, like data quality, cleansing, and curation. And last but not least, obviously, security. More specifically, the implementation of data access, the definition, implementation, meaning enforcement of data access policies that in a hybrid ecosystem may even go as far as geosensitive policies. For example, if you're running your system in one country and you're trying to run analytics or access data that sits on another country, where there are specific geosensitive policies that prevent that data from actually crossing those geo boundaries, and auditing. Fundamental in this equation, as I explained earlier, is data virtualization. And what is data virtualization? I like to again rely on Gartner for this. This is a definition that is a few years old, but I think it's as relevant and valid today as it was back then. And fundamentally, data virtualization is really two layers. The most basic, it's data federation, which provides that plumbing, that connectivity to your remote data sources. But then what takes a data federation into the next level to become a data virtualization solution is the ability to create that abstraction layer. So that means that every data virtualization out there necessarily is a data federation solution. But it also means that not every data federation solution is truly a data virtualization solution. IBM brings all of this together through our platform, Cloud Pak for Data. This is where we implement our data fabric. And I have called out in the description some of the key components of this fabric. The data access layer or query access layer, what we call data virtualization. Watson Knowledge Catalog as a global catalog, single source of truth. Data privacy, advanced data privacy policies that are enforced across the ecosystem, and where ETL and data movement is required, solutions like data stage and data replication. come into play. Next, I would like to illustrate these concepts with what better way than a actual customer scenario. And this very quickly is a global telecommunication company that is right now in the midst of actually evolving their current data lakes to a data fabric using our data virtualization solution. What they have been able to do is actually truly eliminate a number of their consolidated data lake environments using Hadoop technologies and replace them with a data virtualization fully governed layer as part of the fabric that allows their users on the right to directly access the data from the data sources on the left without the need for complex and expensive ETL jobs and without the need to implement, maintain, and evolve complex centralized data repositories. Quickly, let me move on now to a demo of this technology, and this demo will cover data virtualization as a service, which IBM makes available today on IBM Public Cloud.
Data virtualization provides the ability to view, access, manipulate, and analyze data across many systems without the need to understand its physical format or location, and without having to move, copy, or replicate it. With data virtualization, you can simplify your analytics and make them more up-to-date and accurate because you are querying the latest data at its source. Delivered on IBM Cloud Pak for Data as a Service, data virtualization offers the basis for governance and getting insights into your data with direct integration with other services included in IBM Cloud Pak for Data. Let's look into some of the major features available in data virtualization as a service delivered for IBM Cloud Pak for Data. The most common mechanism for virtualizing data is to create a table view or virtual table to segment, subset, or superset of columns, or combine data from one or more tables from different data sources. In this demo, we'll create two connections to two different databases, one for DB2 and one for MongoDB. Then we will join two tables from these data sources to create a virtual view of the combined data. First, let's get to the data virtualization service. From the Welcome page, use the navigation menu in the top left corner to get to Data, and then Data Virtualization. The menu at the top of this page has lots of key resources. We'll start on the Data Sources page. We're going to create two new data sources. First, let's create our first connection to a DB2 database. Click Create New Connection to see all the data sources that are available to connect to. Here, you'll see all the different data sources that are supported, including those from IBM and major third parties. Select the IBM DB2 database data source type and enter all the required information, including a name for your connection and your credentials. Click Create. The connection for DB2 is created successfully. Next, let's create a second connection for a MongoDB data source. Same as before, select the data type, provide all of the required connection information, and then click Create. Now, let's create a virtual view by joining two tables from these data sources. Go back to the Service menu and select Virtualize. Here's where you create virtual tables by combining data from one or more tables. You'll see a list of all of the tables that can be discovered from data sources through all of your defined connections. To narrow the list down, you can filter by data source types and database names, as well as table name, schema, and column. Let's select the customer_demo churn and the activities tables, which are from our DB2 and MongoDB data sources respectively. Click Add to Cart and then click View Cart. This sets up the objects to be virtualized. Now, let's create a new schema for these new virtualized objects. In the Schema column, create your new schema and select it for both tables. Then, click Virtualize. When that finishes, click View My Virtualized Data. You'll notice that you are in a new page in the Service menu, and your two new virtual tables are at the top of the list of virtual objects. Let's select the two new tables and click Join to join them together. From these tables, you can select which columns to be included in the virtual view. Let's join the tables by the ID column. You can click Preview to check that columns are properly joined. You'll be warned if you joined columns of different data types, and you can easily fix them. You can filter the joined data with simple clause statements. You can also use the SQL editor to create a complex view instead of using the UI. Next, assign a name and schema for this view. You can also change the column names if needed. Click Create View. The view is created successfully. Let's preview it. From the Overflow menu on the far right of your joined view, click Preview. You can check the view structure, such as column name and data type, metadata, and the complete SQL statement that created this view. Finally, back in My Virtualized Data, click the Overflow menu and manage access. You can control access to this virtual view by specifying which users can access the view or which roles, such as manager, steward, engineer, or user, can access the view. Your virtualized view of data from two tables in two different databases is now ready for you to use. You can run queries against this virtual view just like you would query any of the original tables. For example, you can secure this data in a data governance application such as Watson Knowledge Catalog, analyze it in a Jupyter Notebook in Watson Studio, or apply business intelligence to it in a Cognos Analytics dashboard. The Data Virtualization Service also provides a dashboard for monitoring, managing the performance of your instance, and exploring the service instance. This monitoring and exploring dashboard is provided by IBM DB2 Data Management Console. We have seen how data virtualization, delivered on IBM Cloud Pak for Data as a Service, provides the basis for governance and getting insights into your data with direct integration with Cloud Pak for Data as a Service. It is available as an on-demand licensing and delivery model with the following major features. You can easily and securely access data across many data sources. You can create virtual objects, manage data source connections, virtualize data, and join virtual tables and views and consume them. You can manage access to objects with defined roles. You can monitor and explore data virtualization through the console provided by IBM Cloud Pak for Data as a Service. For more information, visit us at the links shown here.
Thank you. That was the end of our demo. So as a summary, and we come to the end of the presentation, we briefly cover some fundamental data analytics concepts and state of the current technology. And we talked about the last decade, in particular around the implementation of data warehousing solutions in the form of physical data lakes that leverage open source technologies like Hadoop. We talked about the evolution of those data management solutions into the age of data fabrics and hybrid data ecosystems. We talked about how to address data access requirements across the fabric. We implement a query access layer built on data virtualization that allows us to access all of the heterogeneous, potentially geographically dispersed data sources. And last we did a demo of data virtualization as a service as available on IBM Public Cloud today. With that, we come to the end of the presentation, and thank you.